SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to lecture 11, and today we are going to discuss a new concept, that is of the strain. Okay. So, till now we talked about stress and we now start with strain. So, in our schools we have come across this concept. Let me start with that example. So, suppose we have a horizontal bar and we apply a force F to this bar and we measure the change in length. So, the original length is L, the big L. After we have applied the force, let us say the length becomes small l. So, after deformation the length is small l, then we say that the strain in the bar is change in length over the original length. So, for this particular example, this becomes small l minus big L divided by L, which is, you could also write as delta L divided by L. Okay. So, I think we all have learnt about this in schools, and this strain is also called longitudinal strain, because it is measuring the change in length. So, this is basically longitudinal strain. And it is denoted by epsilon. All right. See, we have only one strain for the whole bar. So, this is kind of global strain for the bar. You know, think of another example. Let us say we have a hanging bar, which is hanging and the weight of the bar is also there. Okay. So, in this case, if you measure strain by tracking the change in length of, let us say, line elements at two locations, one is at the point where it is clamped close to it, and the other is at the other end. Okay. So, this is a vertical bar and gravity is acting this way. So, if you measure the change in length of these two line elements, you will see that the lower line element, so this line element undergoes small change in length, whereas this top one, this goes large change in length. So, basically in this example, the change in length is not the same for different line elements of the bar. So, it is basically varying in the bar. So, in general the strain need not be the same. So, this is called local strain. So, in the first case the change in length for every line element is the same. So, the local strain is same as global strain. So, here local strain equals global strain. which is the total change in length of the bar divided by the total length of the bar. But in the bottom example, in this example, the local strain does not equal the global strain. Okay. So, the take home message is that strain basically varies from point to point in the bar. Just like stress, stress in the body was varying from point to point, the strain also varies from point to point. Okay. You see, this was for a bar, but our body in general does not have the shape of a bar. It could have any arbitrary shape. For example, think of the body having this shape, and you are applying, let us say, external load on this part of the body, and further it is clamped at somewhere else. So, what will be strain for this body? So, you might ask, okay, let us do change in length by length. So, which length do we take here, right? So, there are so many lengths here. Do we take this length question mark, or do we take this length? So, there are basically so many lengths. So, the concept of strain for a 3D body as against a bar is a bit complicated, and there are many kind of strains you learn later on. For example, we have this longitudinal strain is there, we also have what is called shear strain, we also have volumetric strain. All right. So, let us concentrate on just the longitudinal strain. Now, from the basic definition for the case of a bar, we saw that it is actually measuring the change in length over the original length, and you also saw for the case of a vertical bar that we thought of local strain. So, at some point we drew a line element and we started tracking how the length of that line element is changing. So, likewise in the 3D case also, we can think of this body which can be subjected to any arbitrary load, and then we go at any point in the body, let us say at this point, and think of line element at that point in the body. So, there are several line elements at a point in the body. For example, this is one line element, then this is another line element. So, these are line elements now, do not think of them as a plane. When earlier we were thinking of traction, we thought of them as planes, but now we are thinking of them as lines. Okay. So, they are line elements. So, you can think of material along that line, and that becomes the line element of the body. And as the body deforms, that line element will undergo change, is not it? So, when the body deforms, after deformation, suppose it becomes of this shape, then the black line element, for example, it could become curved, is not it? And the red line element could also become something like this. But if you take the lines to be very, very small, but passing through the point, then after deformation the curve can be approximated also as a line, is not it? So, if you take a small line here, let us say a very small line, then here after deformation it would also almost look like a line. So, then track the change in length of these line elements and associate strain with those line elements, is not it? So, basically, so in the 3 dimensional case, at any point in the body, think of small material line elements. So, material line elements means they are connected with the body. So, as the body deforms, the line also deforms. So, therefore, we call it material line element. Think of small material line elements passing through that point. And track its change in length. And with this way we can then define strain at any point in the body. Now, you see at any point we have so many lines passing through it. So, for each of the line elements we have its own strain. So, therefore, the strain, or let us say the longitudinal strain epsilon, not only depends on the point where we are measuring the strain, it also depends on which line element we chose. Now, how to define the line element? We can simply define it by the orientation of the line element, the direction of the line element. So, that we will denote through n. Okay. Contrast this with the traction example. In case of traction, we had T, which was also a function of the point and the surface normal. So, there this n was surface normal. But now, with in case of a strain, the n is the direction of line element. Okay. So, now with this concept we will like to exactly find out the formula for the strain. See, right now it is just an abstract definition and we know what all it depends on, but we would like to find out a formula for the strain in terms of let us say the displacement in the body. So, a body once it gets deformed, every point in the body undergoes some displacement. So, we would like to obtain formula for the longitudinal strain in terms of displacement in the body. Okay. So, let us try to derive that formula now. So, we will call it as formula for longitudinal strain. Okay. So, we have to have a reference configuration relative to which we are going to measure the displacement in the body or the deformation of the body. And the reference configuration could be the configuration at t equal to 0, or it could be the configuration when there is no load acting in the body. Okay. So, suppose this is our reference configuration, and after deformation this is the deformed configuration. Okay. So, I will write here this is reference configuration, whereas this is deformed configuration. And think of a coordinate system here, and the reference configuration, as I told you, is the configuration at, it could be at t equal to 0, or it is the stress free configuration. So, basically it is some configuration relative to which you have to measure the displacement in the body. Okay. Now, any material point in the reference configuration, say it is here, we will denote by the letter big X. Okay. So, that is the position vector of any material point in the reference configuration, and the same material point will go to another point, say small x, in the deformed configuration. All right. So, there is a correspondence here, is not it? Every point in the reference configuration will go somewhere after the body has been deformed to a point small x. So, we can think of a function which will relate the points in the two configurations. So, suppose that function we denote by this f. So, that function is going to depend on the original position of the particle and also the time. So, as time changes, the body is also undergoing some deformation, it is moving from one point to the other. Therefore, this f, the correspondence between deformed and reference configuration, is a function of time. So, basically we can now write that small x, the position in the deformed configuration, equals this function f, which depends on big X and the time t. Okay. And you see this function is basically a vector function. Because it is giving me the final position of any point, and the final position has got 3 coordinates in 3 dimension, small x1, small x2, small x3, right. Therefore, it is supposed to be a vector function, and it depends on big X, which is also a vector, because any point in the reference configuration will have 3 coordinates, big x1, big x2, big x3, is not it. So, if I try to write this in component form, we could also write it as small x1, small x2, small x3. So, that is equal to the function f1, the function f2, the function f3. So, f has got 3 components, f1, f2, f3, and each of the functions depends on the 3 components in the reference configuration. Okay. So, this is the column form of the formula that we have here. Okay. And if somebody asks you what is the displacement, so displacement is simply final position minus the initial position. So, that is going to be, if you just join big X to small x, that is your displacement. Right. So, the red line here is the displacement, which we will denote by u. So, displacement is also a vector quantity, therefore, with u you have a tilde below it, and then the displacement depends on big X, that means which material particle. We are measuring the displacement of which material particle, therefore, it depends on big X and also on time, because with time the particle may be changing. So, the displacement is also changing with time. Okay. So, in terms of the notations that we have introduced here, you could write that the displacement u of big X comma t is actually small f of big X comma t minus big X, right. So, that is simply the displacement. All right. So, now with these notations introduced, we can think of finding out the formula for the longitudinal strain. Okay. So, let me again draw the two bodies, one in the reference configuration and the other in the deformed configuration, and think of a point in the reference configuration denoted by big X and another point very close to it which would be big X plus some, let us say, delta x. Okay. Let us say this point is your point y. All right. So, we have 2 points big X and big Y close to each other. So, with 2 points, when you join them, you get the line element, is not it? So, the materials passing through this line forms your material line element, and then we can think of seeing how this line element is changing once it gets deformed. So, after being deformed, big X will go to small x, right, and the big Y, the other point, that is going to go to small y, is not it? And we could say that small y is actually small x plus delta times small x, right. Just like big Y is big X plus delta times big X, here small y is small x plus delta times small x. Now, the material line that we have originally, which is a straight line, will in general not be a straight line. So, it will become, let us say, curved, but as the 2 points get close to each other, the curved line will start looking like a straight line. And as we want to measure the longitudinal strain at a point big X, so we have to think of line elements which should be associated with the point big X. So, you will see later on that we will make this delta x go to 0. So, that the line element is actually at the point big X, and with that trick we can then find out the strain at the point big X. If the line element is not small, then the strain that we get is not for the point big X, it is for the neighborhood of the point, but we want specifically the strain at the point big X. So, I will just write here that in general the deformed line element will be curved, but as the length of original line element, which is actually big Y minus big X, that is also equal to delta big X. So, as the length of the original line element decreases, the deformed curved line starts to look like straight line. And not only this, decreasing with this trick, of letting the length of the line element, which is delta x, going to 0, we will also be able to measure strain at the point big X, right. Otherwise, the strain that we get is not for the point big X, but for the neighborhood of point big X. So, what we have to find out basically, the strain, for example, at the point big X and let us say some direction n for the line element, we find out the final length, which is delta small x, subtract the original length, which is delta big X, and then divide by the original length delta big X. So, you have to do it and also take the limit delta big X going to 0, is not it. So, with this formula you will be able to obtain a strain at the point big X, right. Let us try to obtain that in terms of displacement of the body, all right. So, what is delta small x, for example, what will that be equal to? So, delta small x, from the picture you can see it is relating y and x, little y and little x, is not it. So, that is little y minus little x, and based on this function small f that we have introduced, we could also write this as small y as small f of big Y, right, and small x is small f of big X. And then we write this big Y as big X plus delta big X, and then subtract small f of big X. And now, we have to do Taylor's expansion of the first term here. See, the argument is big X plus delta big X, and delta big X has got the 3 components delta big X 1, delta big X 2, delta big X 3. So, this has got 3 components. We can now write it as del f by del big X 1 into delta x 1 plus del f by del big X 2 into delta x 2 plus del f by del big X 3 into delta x 3, and we also have to have the first term here, that is the f itself at big X plus the derivative term. So, that is the Taylor's expansion, plus we also have the extra terms, is not it, and then we have to subtract minus f of big X. Okay. So, this whole thing here is basically the Taylor's expansion. Okay, and you can see that the first and last term here cancel, right, and also try to look at the remaining 3 terms here. Can we write it somehow in terms of matrix vector multiplication? Then yes, we can write it, and it would be, think of a matrix whose first column is del f over del big X 1, the second column is del f over del big X 2, the third column is del f over del big X 3, okay, and we multiply this with the column of the delta x, which is delta x 1, delta x 2 and delta x 3, plus the dot dot dot, the higher order terms. Can you think of what is that higher order term going to look like? Just think of one of the terms here. For example, we will have del 2 f over del x 1 del x 1 into delta x 1 whole square by 2, is not it? That is one of the terms. Then you will also have del 2 f over del x 1 del x 2 into delta x 1 delta x 2. Likewise, you have many other terms. Now, what can you say about these terms? You see the numbers here, it is delta x 1 square or delta x 1 into delta x 2. So, is not it proportional to the, or let us say it is of the order of the square of length of delta x. So, basically what I mean to say is that these numbers, are not they proportional to delta x magnitude square? When you find the magnitude of delta x, it is delta x 1 whole square plus delta x 2 whole square plus delta x 3 whole square, and then you have a square root, and here you have another square. So, this is basically delta x 1 square plus delta x 2 square plus delta x 3 square. So, it is basically the quadratic combinations of individual components. The red circles that you have here, you see these ones and these ones, they also have quadratic combinations, and then you have even higher order terms del 3 f by del x 1 del x 1 del x 1 into delta x 1 whole cube by 3 factorial, is not it. So, they are all higher order terms. So, can we club them all together and simply say, so the whole thing together will say it is of the order of big O of magnitude delta x square. So, you are aware with the big O small o notation, is not it? We introduced this when we are doing the linear momentum balance and angular momentum balance. You could also write this as small o of magnitude of delta x itself. So, big O delta x square means it is of the same order as the magnitude square. Also see what can you say about this matrix here. Look at this matrix. So, if you write it in component form, the first column is basically del f 1 by del big X 1, then del f 2 by del big X 1 and del f 3 by del big X 3. Likewise, for the other columns. So, if you just say this matrix to be some f matrix, then f I j, so f I j is simply del small f I over del x j, the derivative of f I relative to x j, and you see it is a matrix. So, in the tensor form it is a second order tensor. So, it turns out the matrix that you have here is actually what is called the gradient of small f, and the gradient is defined in the following way. So, this is simply del small f by del x 1 tensor product E 1 plus del small f by del x 2 tensor product E 2 plus del small f by del big X 3 tensor product E 3. So, it is a new definition here, that is the gradient. So, gradient of anything, this is the formula. You know, I guess you are familiar with gradient of a scalar quantity which gives us a vector. So, if you do that here, you know, say gradient of a function f, but that is just a scalar, therefore, there is no tilde below f, gradient of f. So, that is you apply this formula here, this is del f by del x 1 into E 1 plus del f by del x 2 into E 2 plus del f by del x 3 into E 3. Now, this is a tensor notation. If you represent this in a coordinate system, let us say E 1, E 2, E 3 coordinate system. So, the vector grad small f in the E 1, E 2, E 3 coordinate system then becomes del f by del x 1, del f by del x 2 and del f by del x 3, and this column form is something we are familiar with for a gradient, is not it. So, that is the column form of gradient. Whereas, this is the vector form. Okay. And this definition that we see here in the red, this is the gradient of a vector. So, this is gradient of a vector, whereas in the below we have gradient of a scalar. Okay. All right, so some new definitions here which you have to digest. You see this big F, which is gradient of a small f, we could also write this as summation over I j del f I over del x j of E I tensor product E j. Okay. And we know from the first lecture that the coefficient here forms the matrix components, is not it. So, they form the components of matrix of the tensor. All right. Now, look here again, this expression in blue color. So, we have a matrix multiplied with a column, and see from the first lecture where we talked about vectors and tensors. So, whenever we have a matrix multiplied with a column, its tensor form is simply the second order tensor of the matrix multiplied with the vector of this column. Now, can you see what is a vector of this column? So, is not it simply delta big X, the vector delta big X, which is expressed here in E1, E2, E3 coordinate system, right. It has those three components, delta big X1, delta big X2, delta big X3. Okay. So, finally, after all this new notations, we can simply write delta small x equals the second order tensor big F times delta big X plus some higher order term big O delta big X whole square. Okay. So, it is a compact form because we are using tensor, of course. If you go back to the matrix form, then of course, it is no more compact. So, let me also write down the matrix form here. So, in E1, E2, E3 coordinate system, we have delta small x 1, delta small x 2, delta small x 3, that is equal to the matrix of the second order tensor big F, which has del small f I over del big X j, these derivatives, times delta big X 1, delta big X 2, delta big X 3, okay, plus the big O delta big X whole square. And just for introducing this notation, we also call this big F as deformation gradient tensor. This big F is the gradient of small f, and small f is the deformation. It is also called deformation map. So, gradient of the deformation map gives me deformation gradient. All right. So, once we have this delta small x, what will be the final length? So, final length small l square, is not that delta small x dot with delta small x? And now, based on what we derived already, we could also write this as big F delta big X plus big O delta big X square, this whole thing dotted with the same thing, is not it? It is the same thing here. So, we have to do the cross multiplication, we get 4 terms here. The first with the first there gives me f into delta big X dotted with f into delta big X, right. What do the remaining terms give us? See, we have f into delta big X multiplied with big O delta big X square. So, one of the terms is of the order of delta big X square and f delta big X is of the order of delta x itself. So, when you multiply them, it becomes delta x cube, right. So, the whole thing, the remaining all the 3 terms can then be written as big O delta big X cube. There is one big O delta big X square into big O delta big X square. When you multiply, it is delta big X to the power 4. So, it is all here in this big X cube. When you say delta big X cube, it means it has delta big X 4, delta big X 5, delta big X 6, everything is there, all right. Now, what can we say about the original length? So, the original length, if we say big L square, so that is delta big X dot with delta big X, is not it? Okay, so, now what can you say about the, let us say, the stretching in that line? If we do not stretch by lambda, then what is lambda square? So, lambda denotes the stretch. So, lambda square is then simply the final length square divided by original length square, right. So, that is the square of the stretch. It is not the strain, it is the stretch. So, stretch is simply final length divided by original length. Okay, so, based on the formulas that we have already, we could write it as big F delta big X dotted with big F delta big X divided by delta big X dot delta big X, right, plus big O delta big X cube divided by delta big X dot with delta big X. Okay, now we can do some tricks here. See, this delta big X dot delta big X is the magnitude square. So, it is modulus of delta big X into modulus of delta big X. So, what we will do is we also write it as big F delta big X divided by mod of delta big X dotted with big F of delta big X divided by mod of delta big X. Could you see this? You see the denominator here, this denominator is actually delta big X whole square. So, there are 2 of mod of delta big X, and I simply bring those 2 delta big X separately, is not it? And what happens to the next term here? So, when you divide the delta big X cube with delta big X square, it becomes delta big X, right. So, this becomes big O of delta big X, isn't it? Okay. Now, what can you say about this term here within the bracket? What is this? The vector delta big X divided by its magnitude, right. So, it is divided by the magnitude. What does this give you? It gives me the direction of that vector. So, it is the direction of that line element. You see this in this figure, the direction of that line element. So, direction, that is delta big X divided by magnitude of delta big X, which we can say it is, let us say, small n. Okay. So, finally, in our formula what we have is the direction of the line element. So, depending on which direction you want to measure the stretch, you have to put that particular direction here. So, supposing we call it by n. So, this is direction of line element So, we could write it as big F into n dotted with big F into n plus big O times delta big X, okay. And that is your lambda square at the point x and for the line element with direction n, all right. And you remember our goal that we want to derive it in terms of the displacement. Now, in this formula that we have here on the right hand side, we have big F. So, big F is the gradient of the deformation small f. So, somehow we have to write this big F in terms of displacement, right, u. So, how can we do that? You remember that the deformation small f, which was equal to small x, we could also write it as big X plus u, is not it? Or in the component form, you could say f I is big X I plus u I. U I is the ith component of displacement. So, what will be del f I over del x j? That is simply del big X I over del big X j plus del u I over del big X j. But what is del big X I over del big X j? See, big X 1, big X 2, big X 3, they are the coordinates in the reference configuration of the body. So, they are independent of each other. So, when you take the derivative of x 1 with respect to x 2, you get 0, of x 1 with respect to x 1, you get 1. So, we could write this as delta I j, the Kronecker delta that we had earlier, plus del u I over del big X j. You see, this is in the component form, and if you think of the corresponding tensor, so the left hand side del small f I over del big X j is basically the second order tensor, is not it? It is the deformation gradient. So, we can say it is big F, which is the gradient of small f, and the right hand side delta I j. What is the tensor of delta I j? It is the identity tensor, you remember from the first lecture, it is the identity tensor, and then del u I over del x j is then simply the gradient of displacement. So, this is your displacement gradient. Okay. So, we can bring this formula for deformation gradient in terms of displacement gradient in the above notation for stretch. So, that means lambda square at a point x and for the line element in the direction of n is simply identity plus gradient u into n dotted with identity plus gradient u into n plus big O of delta x. Okay. So, we have basically the formula in terms of displacement now. So, we have to remember an identity which says, so I will just do it in the side. So, for a second order tensor A times the first order tensor small a, and if you dot it with B, then this simply becomes small a dot with A transpose times B. So, when you bring this second order tensor on the other side of dot product, it becomes transpose. Okay, this is an identity, all right. So, look here also, let us say I want to bring this on the other side. So, what should I do? I have to transpose it, right. So, this becomes small n dot with identity plus gradient of u transpose into identity plus gradient of u times n. So, this whole thing is together plus this big O of delta x, and let us expand this now. So, this is n dot identity plus gradient of u transpose plus gradient of u plus gradient of u transpose into gradient of u, and this whole thing has to be dotted with n. So, this thing inside the bracket is basically this whole thing is the product of the two tensors here. Okay, so, with this formula I am going to stop here and we will continue from here in the next class, okay, where we will find out the formula for the longitudinal strain, and we will also talk about what is called shear strain. All right, thank you.